Another technology where you have to have at least a basic understanding is called spread spectrum. So what is the problem? Let's have a look at the transmission. Let's assume you transmit a signal using a certain part of the spectrum. That usually, we learned this, creates, if you have the spectrum here, this peak, this is where you have your signal, a narrowband signal. Now think of certain type of interference destroying this narrowband signal. So you have interference, narrowband destroying this. Then you will lose your complete signal. So-called frequency depending fading can simply wipe out your narrowband signal for the duration of the interference. So the basic idea now is, why not spreading the signal? Instead of transmitting this only narrowband signal, you spread the signal over a much larger part of the spectrum. So you spread the narrowband into a broadband signal using a special code. I will come back to this in the next chapter when I talk about CDMA technology. And then the signal is protected against narrowband interference. Why? Look at the figures. Blue is our spread signal, and this purple is our narrowband interference. This interference then wipes out a part of our spread signal. But you have here enough energy, enough of the spectrum you use for a signal to reconstruct not the original signal, but quite a good signal on the receiver side. So the receiver does something magic, I will explain it in a second, and tries to reconstruct the original signal. It despreads the signal, the received signal, which contains the spread original signal plus the interference, and the result is a spread interference and a nice narrowband signal. I'll just show you this in a bit more details. So the interesting part is, it all depends on the code, how you do this spreading. There are different versions, different technologies, direct sequence spread spectrum or frequency hopping spread spectrum, both used in real systems. And depending on the code you apply for spreading on the technology, you can have several signals in the same space, the same time, without dynamic coordination. And it's even tab proof. If you do not tell this code to anyone, well, you cannot listen into the communication. So just to give you a bit more insight, remember, this is not a course for electrical engineers, this is for computer scientists. But you as a computer scientist, you should have a basic understanding of these technologies, because they directly influence the performance of the system in terms of bits per second, latency, what we can do with it if we then later on talk about applications, protocols, etc. So now, let's start with the sender. The sender wants to transmit a certain user signal, simplified, idealized, here shown as dark gray block. So you put a certain amount of energy here in this block, so that's the area, this rectangle. I know in real systems it doesn't look exactly like this, but this is basically, okay, this is the signal I want to transmit. It's narrow band because you use only a small part of our spectrum. Now you perform the so-called spreading. So this is our spreading of the signal. How we do this, I will explain in the next chapter. We use a certain code. We could, for example, multiply our data X or etc. So we spread it. Then we have a spread user signal. Now we transmit the signal over the air. Well, you know we don't need air, but okay, we transmit over the air. The result is a signal that contains the spread user signal, dark gray, plus a broadband interference, so background noise from whatever source, plus now our narrowband interference. So we assume a narrowband interference. That's our narrowband interference. Then this narrowband interference destroys a certain part of our spectrum. So now we have to reconstruct our original signal. So what we do is we perform a despreading, but we have to know the code. So we have to know how we actually spread the signal, then we can perform the despreading. So we despread this mixture of signal, user signal, broadband and narrowband interference. And now the trick here is that the despreading recreates a narrowband user signal, and only the user signal is narrowband afterwards, because as we will see, the despreading code has to fit to the spreading code. Only if you know it, you can despread this user signal. What happens to the broadband interference? The broadband interference stays broadband. Well, you do not create a narrowband interference out of broadband. What happens to our narrowband interference? You actually spread the narrowband interference into broadband interference. So this raises the noise level here. As you see, you add the white narrowband interference and the light gray broadband interference, but you still have a user signal. The next step is you apply a filter that cuts certain frequencies. So you cut off the higher frequencies and the lower frequencies. We don't use them. And then the hope is that in the end the energy you receive from the original user signal, so the dark gray part, is big enough to detect the original data. And yes, you will have some noise, but these are only parts of the broadband interference and parts of the narrowband interference. So the narrowband interference will not cancel out the complete original user signal. That's the basic idea of spreading, how to counteract interference. So yes, your user signal still has to be strong enough to be detected. So you have to have still a good signal to noise ratio. You have to be able to detect the original signal. You will have some noise in it. So that is the idea, and just to give some more examples that you better understand it. What happens if you have this frequency selective fading or a narrowband interference? The effect is basically the same, and you apply spreading. Well, the upper figure shows you the classical FDM system. So you have a frequency division multiplexing with guard spaces and narrow bands for different channels. Channel 1, 2, 3, 4, 5, 6. So 6 channels, and we just assume a certain pattern of fading or interference, and it hits hard channel 3 and 4, and maybe you will receive something from channels 5 and 6. Maybe there's a certain threshold, so signal strength must be above this limit. So that's one of the ideas. Then this channel now has problems for 3 and 4. What happens if you use spread spectrum channels? You spread out all the channels using a way larger part of the spectrum. Then still this fading hits parts of the spectrum, so you will wipe out parts of our channels, but the remaining parts are enough to recreate the original data. So that's the idea. How we do this coding, how we do the spreading, I will come back to this. But that's the basic idea. So we're now way more robust against frequency selective fading. Just a side remark, the channel quality shown here as thicker black line, this changes over time. So you do not know now exactly which frequency is hit by this frequency selective fading. This changes over time. This can change within microseconds, milliseconds, whatever. It can change if you use your car, you drive around in cities, etc. So you always have this frequency selective fading problems. And there may be some different sources for interference, etc., etc. So now, how do we do the spreading? There are two basic technologies you can use. One is called direct sequence spread spectrum, or DSSS. So what you actually do is you XOR your signal with a so-called chipping sequence. The chipping sequence might be a fixed pattern or a pseudo-random number sequence. You can use just some so-called chips for your chipping sequence, or many chips per bit, 128, 256, etc. The more chips you use per bit, the higher the bandwidth of the resulting signal will be. So, example, on the right hand side you see two user bits. These are our bits. This is a level where we talk about bits. So 2 bits. Each bit has a duration of TB. And now we apply a certain chipping sequence. In this case, we have a fixed chipping sequence. We apply this fixed chipping sequence here. So that's just an example. So we have a chipping sequence of, in this case, 7 chips we apply on each bit. So the chipping sequence will thus create a 7 times higher bandwidth of the signal. 7 times higher compared to the original bandwidth we need for our narrowband signal. So this is all done in the digital domain. So we simply XOR our bits with a chipping sequence, creating a chip stream of chips with, in this case, 7 times more chips per second compared to bits per second, resulting in a 7 times higher bandwidth requirement. So we have a resulting signal, and this is actually the spread signal. And the interesting part is you have to know the chipping sequence to reconstruct the original data. In this case, it's quite simple, 7 chips, but in real systems you can have many more chips depending on the quality and how much spectrum you have, etc. Big advantage, you reduce frequency selective fading, and the interesting part here is also so you can reuse the same frequencies, but you may use different chipping sequences, and thus you can transmit at the same time same frequency signals. They overlap. I will show you an example in the next chapter. They will overlap, and you can still recalculate the original signal out of this mishmash, this mixture of different signals. And with the help of these technology, we can also perform something that is called a soft handover. I will come back to soft handover when I talk about 3G, classical 3G systems. We also have a problem. This is again a pointer forward to when I discuss these technologies. We need precise power control. Precise power control, that means if a receiver receives many different signals, they all overlay, you get this mixture of signals, but the strengths of the signals from different senders should reach the receiver more or less the same power level. So that means, let's go back to our party example. So if you're there, you want to receive something from 2 persons in the room, and if one person standing closer to you is crying very loud, you will not be able to understand anyone else, no matter how good they code their data, if they use different language, which isn't different code. So that's a problem. But if all the signals reach you roughly at the same power level, it's way easier to distinguish between the different receivers. So that's the basic idea. Just to make the picture complete, a simple block diagram. So if you have your direct sequence, your DSSS system here, you start with your user data. These are our ones and zeros, etc. You apply, that's a pure digital system, you apply your chipping and you already get your spread spectrum. Then you do your digital modulation and your analog modulation, you use your radio carrier and you transmit your signal. On the receiver side you receive it, you do the demodulation, well, you know the radio carrier, and then you have to know the chipping sequence, and then we do something that's called a correlation. A correlator recalculates the original data. How this is done, next chapter, I give you some simple examples. We have to decide, was this a 0 or 1, and we can recreate the data. So for this part, wait until I reach chapter 3. But these are the very, very, very basic steps. We find these technologies in many of the 3G systems. Then there's also another way of how you can spread the spectrum. You simply jump around in the spectrum, a very fast pattern. So you have discrete changes of the carrier frequency, and the sequence of these frequency changes, they are again determined via a, for example, pseudo-random number sequence. That's one of the ideas. So there are different versions. You can have different frequencies for a symbol, or you can have several symbols per frequency, or here written as per user bits. So fast hopping schemes, slow hopping schemes. Slow hopping, that means you stay on a frequency, you transmit, we are computer scientists, you transmit many bits on this frequency, then you jump to another frequency. And for fast hopping, well, actually you jump through frequencies while you just want to transmit a single bit, for example. That would be an extreme case. Big advantage, it's a very simple scheme, very simple. I will show you in a minute how this works. And besides being simple, at any time you use only a small portion of the spectrum. Remember, direct sequence spread spectrum smears the signal over a way larger part of the spectrum. Here, you jump through the spectrum. At a point in time, you occupy only a small part. Simpler to detect, not as robust as DSSS, are some disadvantages, but this is a classical scheme you use in Bluetooth. The classical Bluetooth system jumps through the spectrum on 79 channels, and you jump 1600 times per second. So that's the idea. So what do you do here? Again, we have our user data. And the first example shows slow hopping. So we transmit 3 bits in this case, staying around the same center frequency, F2. So you see, we stay here and we transmit these 3 bits, so slow hopping. Bluetooth, just to tell you this, although this sounds like, oh, fast hopping, 1600 times per second, it's a slow hopping scheme because you transmit many, many, many bits staying on the same frequency. So, and then for fast hopping, transmitting a single bit, in this simplified case, well, we jump already through 3 carrier frequencies here by transmitting a single bit. So that's the basic idea. And also to show this to you, basically what you need is a so-called frequency synthesizer, and you feed the synthesizer with a hopping sequence. And then This synthesizer basically gives the modulator different carrier frequencies. This means you jump around in the spectrum. On the receiver side, you have to know the hopping sequence, and then you basically follow the hopping pattern. So you feed the demodulator by these different carrier frequencies. So you tune into different carriers all of the time, 1600 times per second, for example, in Bluetooth, and then you can demodulate your original data. So now we've learned a bit about spreading spectrum, about modulation, about multiplexing, so different schemes. And you can imagine you can combine all these schemes. But using new scheme usually requires new hardware, because in classical systems you implemented all of this in hardware. Wouldn't it be nice just to download a new multiplexing scheme, just to download a new modulation scheme? Instead of 64 QAM, I download 256 QAM, so I don't have to buy a new device. Would be nice, but this requires something called a software-defined radio. Software-defined radios are clearly the future to go. What does it mean? In an ideal world, the basic idea is as follows. You want to be completely flexible when it comes to modulation, frequencies, codings, whatever multiplexing, whatever schemes, and you're used to downloading new apps. And similar to downloading a new app, you could simply download a new radio technology. Great idea. So, what does it mean? On the transmitter side, you stay completely digital until the very end. That means your application down here generates zeros, ones, zeros, etc. So, and then, and this is the magic part, you have a signal processor that applies all these modulation, whatever schemes on the digital side and creates with a very high data rate a digital stream of bits that is then directly converted into an analog signal, amplified, and then sent out over the antenna. That's the basic idea. So, you stay purely on the digital side. You use algorithms for doing all this multiplexing, etc. We know these algorithms, so they are all well known. And then, at the end, you basically map this extremely high data rate stream of ones and zeros onto an analog signal using a DA converter, digital analog converter. On the receiver side, well, it's very simple. You receive the whole spectrum. So everything between, let's say, 80 megahertz and 60 gigahertz in theory. So you receive a huge spectrum. You perform an extreme fast analog to digital conversion. That means you have this high data rate stream of ones and zeros, and then you apply all your algorithms that then filter out on the digital side the original data. They apply the modulation and all these things. So a receiver is a very fast AD converter plus a digital processor. So that is the ideal world. The problem is, in the real world, well, first of all, there are no such extreme fast digital to analog, analog to digital converters. There are also no such antennas and amplifiers that cover a wide range of the spectrum. So you cannot use the same antenna and the same amplifiers for 80 megahertz and 60 gigahertz. You cannot use the same analog filters you need, the low noise amplifier, the power amplifiers, all these things. Doesn't work. And you have a lot of interference. So, but still it works in certain domains. So there are different systems, and a very well-known system, for example, is the GNU radio. There are a lot of articles about software-defined radio. So the concept itself is not brand new, so it's known since many years, but the problem is how to really implement this. But this would be the perfect world. So you buy a device and you simply download the newest radio technologies. Okay, some more questions and tasks for you to do. Remember, what are typical means to mitigate narrowband interference? Think of complexity. Why do we do spread spectrum? How can we do the spreading? Once more, you don't have to go into electrical engineering. Stay at a certain level. So think again of the concept of guard spaces, FDM, CDM. What could this mean? Guard space. Then think of DSSS systems and multipath propagation. Look up multipath propagation. What could we do there? So we have multiple paths. Think of different parts of the signal going different paths. What could we do there? How can we benefit? And then please have a look into SDRs today. What can you do with even low-cost SDRs? So if you spend something like whatever 300-400 euros, you can get some decent SDRs and you can play the classical carrier frequencies of wireless LANs, of cellular phones, and you can implement your own base station, your own wireless LAN adapter. You can look into traffic, you can play with it and understand everything way better. So there's a nice link into the GNU Radio project and you will get there a lot of information about this topic.